Right. Today we are going to look at hashing or hash tables. Um, it's also another data structure in computing. So we are going to spend some time to look at it. We'll look at the what hashing is, the problem or the issues you can encounter when you are using hash table, and then we look at how to resolve those issues or algorithms that can help you resolve those issues, and also the performance of those algorithms. Okay. All right. So let's start. Okay. So basically, hashing is a data structure which performs a special function. It's used to basically map a given value to
Oh, yeah, nice.
key, a particular key for faster access of elements. Okay. So if you remember from our meeting last week where we talked about the searching and the sorting um, algorithms, for instance, the searching algorithm, we talked about the linear search. And then we also talked about the binary search. And we said the linear search searched one item at a time from the beginning or from the first element to the last element, okay, until it's able to locate the key value. So in a linear search, worst case, the time complexity is going to be log n, okay, because it has to iterate through the entire array or the entire list. Then we have the binary search, which divides the list or the array into two and searches for the middle value, compares if the middle value is the same as the key value. If it's not, it moves to the left side of the list or the right side of the list based on the value. So if it's, we're assuming that in that case, the list should be sorted and so on. Okay, so that also gives us a, a growth rate, okay, of um, big O of log n. Okay, now the hashing or hash tables also comes in to help you locate a key element in your list, okay, to access it faster. Okay, so faster in this context is we are trying to see if one is giving you log n and the other is giving you n, how can we probably get access an element faster, thereby giving us, for instance, maybe a complexity or a growth rate of, or a constant growth rate. Okay, so that is where hashing comes in. Now, hashing makes use of what we call a hash function. Now, this hash function is what helps you to map the value to a key element. Okay. Now, the efficiency of mapping depends on the efficiency of the hash function that it's used. So if your mapping is going to be efficient, it always depends on the hash function used. So we have an example here. It says, let a hash function be h of x that maps to a value at index n log 10. Okay. So basically what this is talking about is we have let's say this array. I hope you can see my table.
Yes, sir.
Okay.
Yes, sir.
So let's say this is index 0. Index 0, 1, 2, 3, 4, 5, and let's say 6. Okay. So you have this as your table. Then we've been given a function. Okay. So the function is supposed to map x, where x is your given value. So we say that these values over here, which is a different color. Okay. The values we have here are your x values. These are your x values. And we've been given a hash function, which is this. So our hash function h of x our hash function h of x is equal to x mod. So we know the percentage anytime you use percentage in programming. Okay, it's an operator for modulus. Okay, so mod 10. Now, what it means is that we have to pass our value x through our h of x. Okay, now whatever answer we are going to get or result we're going to get, we are going to push that result into our array based on the index. So the result will be based on the index of that particular the index of the table, okay, of our array or our list. So if we take the first value of x, which is 11, we are going to pass 11 through the hash function. So this is going to give you h of 11 which is equal to h mod 10. And what would that give us? 11 mod 10. Anyone?
1.
1. Okay. By the way, please type in your names and index number here as form of attendance in the chat. All right. So this will give us a value of 1. This will give us 1. Then we move to the next one. 12 mod 10. And what would that give us?
2.
Yeah. So that will give us 2. So if we go all the way down to 15 mod 10, that should give us mod 10. That should give us 5. Okay. So these are the values we are getting. So we are going to store the value of x in our array based on the position we derive from our hash function. Okay. So if we take the first value, which is 11, 11 will be stored at position 1 or index 1, then 12, then 13, then 14, and then finally 15. Okay. So that is what hashing is all about. There's always a hash function. Okay, so given that hash function, you are able to store or access a value from your array. Any questions so far? Any question?
Oh, sir, please, I didn't get the last part where you're entering the figures into the table.
So we enter the figures based on the index. So we use the hash function. So for instance, our x is 11. X being 11, we put 11 inside our h of x. That's h of 11. So 11 mod 10 will give us 1. Okay. So this 1 means we are going to store the value 1. We are going to store the value x, which is 11, at index 1. Are you clear?
Okay. Yes, please, I get it.
So we find mode of all the value x, and that will indicate where they should be stored inside the list.
All right, sir.
Okay. So basically this the explanation to it. So 11, 12, 13, 14, 15. We take h of x of each mode of each of x. Okay, so mode 10 of each of them. And then that shows us the position they occupy or they are going to be stored in our hash table. Now, hashing data structure. So suppose you want to design a system for storing employee record keyed using their mobile number. Okay. So you have employee records and they are keyed using their mobile number. So you have employee 1, you have employee 2, and then you have employee 3. Okay, so we assume that they all have their respective mobile number. And in our mobile number, we have how many digits? I think 10 digits, right? 10 digits, right?
Yes, sir.
Yeah.
Yes, sir.
Okay. So this is what it's trying to say. It says we want to follow the following queries to be performed efficiently. So what we do is we insert the phone number and the corresponding information. Okay, we want to search for a phone number and then fetch the information. We want to delete the phone number and then the related information. Okay, so we can perform this query on them. Now, the next thing is that we need to come up with a data structure towards maintain the information of these 3 different phone numbers or employee numbers. Okay, we can also think of it as the list of students, okay, and their index numbers. Okay, so the array of phone numbers and their records, a linked list of phone numbers and their record, a balanced binary search tree with phone numbers as key, and then also a direct table. Now, if you are using an array and linked list, okay, what happens is that we need to search in a linear fashion. So that can be costly in that process. Okay, so searching in a linear fashion, if we use arrays and keep the stored data or the data stored, then a phone number can be searched with a growth rate of log n. based on the binary search. Okay, but the insertion and deletion become costly if it have to maintain the order. Then when it comes to the binary search, okay, or a balanced binary search. Now remember binary search tree, okay, where we said that for a binary search tree, the value of the left side should be less than the root, and the value of the root should be less than the right side of the tree. Okay, so a binary search tree which is balanced should always follow that description. And that will also guarantee an operation of log n. Okay, anytime you use that search. Yes, Ernest, your hand is up. You have a question? Ernest, do you have a question? Okay, so let's go on. So that's also for the binary search. Okay, it also takes log n. Now, then we have the direct access table. Direct access table, which is also another way of handling a list of items. So a direct access table where we can make big array, then use the phone numbers as the index. Okay. Now, in an entry in array is nil if the phone number is not present, else the array entry stores the pointer to the record corresponding to the phone number. Okay. So the time complexity wise, this solution is best among all. Okay, and we can do all operation at log n. So basically what the direct access table is doing is that the phone numbers are more like going to be represented as the index. Okay, they are going to be represented as the index. So what will happen is that we have a key value. So for instance, we are going to say a key value, okay, of 21. So if the telephone number is in that particular aspect, in that particular order of your array, it's going to locate that number in that form. Okay. Now, one key thing we should note is that let me rather use Excel. Let me use Excel to demonstrate this. All right, so I hope you can all see the Excel sheets.
Yes, sir.
Okay, so let's have here employee ID. And let's have here telephone number or phone number. And then let's have here other records. So let's say name and then say address. Okay. So let's take 3 employees. So we say emp1, M2, M3. And then let's take the telephone numbers. So 0244 5566 71 72. And let's take another number. Let's say 05 and then let's take the last number. Say 026. Okay. So we have a telephone numbers, and then let's take the name. So we have this as our list. Okay. Now, what is going on is that we want to store this, okay, using an array. So if you are using an array, we can say maybe the indexing is starting from 0, 1, 2. Okay, and want to locate them in that order. So if you are going to perform a linear search in this context, that means we have to start from 0, move to 1, and then move to 3. If, for instance, the telephone number we are looking for, the key value we are looking for here is, let's say, the number 0244, or let me use the second one, 026 43 0 0059. Okay. So if this is the number we are looking for, okay, with a linear search, it has to go through all the search, okay, and find it. With a binary search, it's going to divide it into 2. So it's going to pick this as the mid. Okay. Then it will compare with the middle number first before doing the other comparison. Then we also have the what's the other one? The balanced binary search tree. So the balanced binary search tree is more like, okay, we have index 0, or we have our binary search tree. So the first one, employee 1, will be the left side. Employee 2 will be here, and then employee 3 in this form. Okay, and we know that for a binary search tree, the value of this side should be less than, this as the root, and the value of the root should also be less than the term employee 3. Okay, so that is what is has been explained here in this particular example. Okay. Then we have the direct access table. Okay. Now the direct access table is a table that uses the key directly as the index. Okay, it uses the key directly as the index. So for instance, if we are using, the key has to be the telephone numbers, what it's going to do is that direct access table is going to convert all these telephone numbers as index. Okay, so for instance, instead of giving it a place in memory where we have this value 0, 1, 2, 3, okay, as the index, if we were to be doing array, in direct access memory, it's going to use these values, that's the telephone numbers rather, as the index of the records that you have. Are you with me?
Yes, sir.
Okay. So that is what is being explained over here. It uses the values. Okay. Now, one advantage of the direct access table is that it's able to search for, it's able to give you a time or a search at a constant time. Okay. So direct access table use arrays which are random access table structure. Okay, so the key values, which in this case is going to be the telephone number, okay, it's also the index, so it can be used easily to search for a record in a constant time complexity, so big O of 1. Now, when it comes to insertion also, you can use it easily to insert the element. Okay, so the same follows, okay, when you look at the use of the direct as address table or access table. Now, the disadvantage comes, or another advantage is when you are performing deletion. Okay, so you delete based on the index, and in this case, the telephone number is the index. So you delete the telephone number, and then that record is gone from your list. Now, the limitations with this is that prior knowledge of the maximum key value. Okay, so you need to know that value, the key value. Okay, you need to know the key value. So in terms of memory, you are supposed to know the direct telephone number before you can delete. Okay, so that's one disadvantage. Then practically, it's useful only if the maximum value is very less. Okay, so you are looking at a telephone number and you are looking at 10 digits inside the telephone number, which is a lot. Okay, so if you want to consider the maximum value, that means, for instance, when you even have to perform a sort of the telephone numbers, okay, you are taking them as actual numbers and you want to sort them. For instance, let me just go back to this Excel. You are taking this as actual numbers and you want to sort them. Okay, you are looking at the first number. So if you are sorting it, probably this will come first, right? In from the least to the largest. Okay, we are going to take this first, followed by this, and then maybe the 05. Okay, because let me just do filter and sort from smallest to highest from A to Z. Okay, so as you can see here, this done the sort for us. Okay, now this is just we working with 3 employees. Okay, imagine we have a lot of employees and then we have to perform that search based on the number. Okay, so that will be a bit difficult because the maximum value is really large. It's looking at, if we want to convert it to numbers, we are looking at billions, numbers in the billions, okay, or millions, yeah. So that's one disadvantage. Then it also causes wastage of memory space if there's a significant difference between the total record and then the maximum value. Okay, so that is also one limitation when it comes to the use of direct access table. Then the solution, or this solution, that's the direct access table, when we look at the practical limitation, we say that the solution, or with this solution, the first problem with this solution is that a huge extra space is required. Okay, so for example, you have a telephone number of n digits. Okay, we will need big O of n times 10n space for the table where m is the size of the pointer to the record, and then n is the digits of the telephone numbers. Okay, so this makes it complex when you are trying to handle the values because you have n telephone numbers. The telephone numbers or the numbers or the digits within the telephone numbers are a lot. Okay, so it's going to be it's going to take a more of some time to be able to handle that particular list or that particular record. Okay. Now another problem is that an integer in programming may not be stored, okay, in n digits. Okay, so that can also be another issue. So due to these limitations with the direct access table and then the other approach that we mentioned earlier, okay, the hashing is introduced to solve those issues. Now, hashing can also get us a time complexity of 1 or a constant time complexity in the search, okay, in the search time. And in other cases or in the worst cases, it gives us a linear time complexity of n. Okay. Now, one key difference between the direct access table and the hash table is that with the direct access table, the direct access table, it's used directly, or the key, in this case, the telephone number is used directly as the index. Whereas with the hash, we have to convert that key, which is the telephone number, into an array index. Okay, and we'll look at how we can do that shortly. Okay, by using the hash value. Then another difference is that when you look at the direct access table, in terms of real world scenario, okay, when using direct access table, it's actually impractical. Okay, its practicality is impractical with real world scenarios, okay, due to issues like memory constraints. Okay, but the hashing table can easily be implemented when you are using your programming language. For instance, in Python, you can use the dictionaries and sets, okay, in Python to implement hash table. But with the direct access table, practically it's impossible. Then when it comes to memory efficiency, direct access table is not, okay, it's highly inefficient, okay, when you are trying to use the telephone numbers as the index or the key to your table. It's highly inefficient. Okay, but with the hashing, it becomes memory efficient because you are using a hash function to generate a hash value, which can be used as an index or an array index in your table. All right, so it said hashing is an improvement of a direct access table. The idea is to use hash that converts the given telephone number or any other key to a smaller number and uses that smaller number as index in the table called the hash table. Okay, so that number will be converted as index to the table. Now, for instance, let's go back to our table. Okay. So what it's saying is that we are going to take this key, which is the telephone number, and then we map it, okay, to a hash function. So maybe our hash function, we can say, let's still go by the same hash function, which is x mod 10. Okay, so we can decide over here that we are going to take the last 3 digits of each telephone number. Okay, the last 3 digits of each telephone number, and that will be our value for x. Our value for x. Okay, so x is going to give us, in this case, we are going to get 672. We are going to get 059, and then we are also going to get 459. Are you all following?
Yes, sir.
Okay, so we are going to get these values as our value of x. Let me make this bigger a bit. Okay, so let's introduce our key. So our key value, so we have the first one is 672. We have the next one as 059. And then the last one is 459. Yeah. Okay. So we are going to pass it through our hash function. I'm just trying to use Excel so that you can understand the entire concept that is being explained. Okay. So our hash function is given by our hash function is given by x mod 10. Are we here? And this our x. This is our x. So what we are going to do here is we are going to pass this function into, we are going to pass the value x into our mod function, okay, to get our hash, sorry, this should be the hash value, to get our hash value, which will be our index, okay. So if we say x, which is this value, okay, times its mod, in this, yes, mod 10. I hope I'm getting it right. Can anyone help me?
Two.
So, okay, I'm just trying to put it in Excel form. So I think let me make this wider a bit. So we have mode. So it's going to take first the number. So this number, sorry, E2, comma, then the divisor, that's the mode. So mode 10. Okay. So that will give us 2. And then 99. Okay. So this is going to be our index. Are you all with me?
Yes, sir.
This is going to be our index. So if we come to our hash table, we have our index. So we want to put it inside our hash table. Let me just say hash table. Hash table. So we have our index here. And then we have our telephone number, or we put our key. So let's say telephone number, the value. It's rather phone number. So let's assume this is giving us 10. So 0 to 9, 1, and then we have the telephone number. So if we take the first telephone number, okay, its hash value is 2. So that means that we are going to store those records at index what? 2. Are you with me? Are you following?
Yeah. Yeah.
Then we take the next
Yes, sir.
telephone number, and that will be stored at index 9.
Hello.
Yes. Justice, you have a question? Then we take the third telephone number. That's also index 9. We have to store that as index 9. Okay. Now, this is where the problem comes in when you are using hashing or the use of hash function. Okay. So you realize that we have a space of a list of 10. Okay, and we have just 3 numbers. However, 2 numbers are taking the same hash value, okay, or the same index. Okay, so that leads to what we call collision. Collision. Why? Because we are getting 2 key values, okay, occupying the same index. So how are we going to handle this? All right, so let's move back to our slides and address this further. So that's what it says. It says that the hash function converts the given number or any key to a smaller number and then uses the smaller number as the index. So like we saw with the hash value. So hashing is applied when indexing database. It's also applied in caching. It's applied in error checking. It's applied in program compilation when you're compiling the program, and can also be implemented in password authentication. Password authentication. Now, the hash function algorithm. Hash is basically a function that converts a given number or a given telephone number into a small practical integer value. The map integer value is used as index in the hash table. It's in simple terms, the hash function maps a bigger number or a string to a smaller integer that can be used as index in the hash table. Now, the properties of a good hash function. One is that it's efficiently computable. And then secondly is that it should uniformly distribute the key. So each key or each table position equally likely for each key. Okay? For example, for the telephone number, a bad hash function is to take the first 3 digits. Okay, so you get a scenario. It's saying that in the context of the telephone number, a bad hash function will be to take the first 3 digits. Now, in this example, you might not see the relevance of that statement, which is saying that a hash function is taking, or a bad hash function will be to take the first 3 digits. Why is that the case? Because we can get another telephone number which starts at 024, right? However, this telephone number will have maybe a change in the value. So maybe 0249. Okay, so just this 9 here is changing. It's making this telephone number different from employee one's telephone number because of what? Just this value. So if you are working with the first 3 values or first 3 digits in this telephone number, and you take this as well, you'll notice that if you in turn want to perform a search, it's going to conflict with employee 1. So let's assume this employee 4. Okay, it's going to produce, there's going to be a conflict because it doesn't know whether you are looking for employee 1 or employee 4. Okay, now another context, okay, if you are looking at this also, the last 3 digits, okay, that will also lead to the same thing, giving you what? An index of 2. Okay. However, there are other means by which you can address such a function. Okay, so we are going to look at that shortly. Okay. But you realize that in this context, the probability of you getting the last 3 numbers different, okay, is getting the last 3 numbers being the same is minimal. Okay, whereas getting the first 3 numbers starting with 024 is very high. In fact, if we take the telcos, for instance, the MTN, you realize that they initially started with the 024 prefix, okay, or prefix code. So you get a lot of the probability of getting people with 024 is very high than getting people with their last 3 digits being the same. Okay, so it's always best you go in with the last 3 digits than the first 3 digits. All right, so you said the better function is to consider the last 3 digits. Now, this may not be the best hash function, okay, because there could be other better ways to do that, just like I explained. Now, the hash table is an array that stores the pointer to the records corresponding to that given number. So an entry in the hash table is nil if no existing telephone number has a function value equal to the index for that entry. Then we talked about, or I gave you a scenario of collision. Now, since a hash function gets a smaller number, okay, for a big key, there's a possibility that two keys will result in the same value or hash value. Okay, so like we saw with the example, employee 2 and employee 3 having their hash value as 9. Okay, so that results in what we call collision. Now, the situation where a newly inserted key maps to an already occupied slot in a hash table is called collision and must be handled using some collision handling techniques. So what are these techniques? There are two main techniques. There is the open addressing, and then there's the chaining technique. So we'll take them one by one, starting with the open addressing. So in open addressing, all elements are stored in the hash table itself. Okay. All elements are stored in the hash table itself. Now, each table entry contains either a record or nil. Nil means those indexes do not have any record. Now, so let me just go back to the Excel file. Okay, so nil means so 0, 1, 3, 4, 5, 6, 7 are considered to be what? Nil. 6, 7, 8 are considered to be nil because they do not store any record or they do not store any telephone number. Now, it says here that at any point, the size of the table must be greater than or equal to the total number of keys. Note that we can increase the table size by copying all data if needed. Okay. And the key thing here is that the size of the table must be greater than the total number of keys. So if you go back to the Excel file, you realize that what our keys, let me just take this out. Okay. So our total number of keys we have here are 3. Okay. However, our table size is what? A size of what? What's the table size? Anyone?
10.
Yes. So our table size is 10. Okay. So it says here that the size of the table must be greater or equal to the total number of keys. So that's one of the key things you should know. Now, when searching for an element, we one by one examine the table slots until the desired element is found. And it is found, or it is clear that the element is not in the table. Now, to search for the element, so insert key, K for key. You keep probing, okay, until an empty slot is found. Once the empty slot is found, you insert K. Okay. Now, this is what it means. So we inserted employee 3, right? That's the first telephone number ending with 9, okay, at index 9. And then we come to Mildred, which is employee 2 with a telephone number also ending with the hash value 9. So that has to be inserted at index 9. Now, what it's saying is that with the open addressing, it says that you are supposed to probe until an empty slot is found. Okay. So what we do is index 9 is already occupied. Okay. So we look for the next available index, which is nil. Okay. So that we can insert the next key or the next record in that particular index. Okay. So if we move from 9, we have to come back to what? 0. Okay. Index 0 is free. So what do? We take this record and keep it at the next available index, which is index 0. Okay, so what we've done here explains the open addressing technique for handling collision in hashing or hash table. You get the concept.
Yes, sir.
Okay. So for instance, if we assume this is employee 4, M4, and we know that employee 4, looking at everything, will also give us a hash value of 2. That means that if we take employee 4's contact and we want to save it at index 2, index 2 is already occupied by employees 1's record. So what do you think will be, using open addressing, what would be the next position to insert
Index.
employee 4's record? Anyone?
Index 3.
Index 3. Okay, index 3. Then if we have another employee who has a number which is giving us a hash value of 2, then that person's value or that person's record will go to index 4 in that order. Are you all here?
Yes, sir.
Okay,
Yes,
so
sir.
that is how open addressing, one of the techniques in handling collision, works. Then we have search. So when it's searching, this also keeps probing until the key, the slot's key does not become equal to K or is empty, okay, or an empty slot is reached. Then in terms of deletion, the operation is interesting in the sense that if we simply delete key A, then we might, the search might fail. So the slots of the deleted keys are marked as deleted. Okay. So for instance, if you are deleting from maybe a telephone number from a particular slot or a particular index, we mark the index as deleted. Okay. Now, then we can insert an element in that deleted slot, but the search does not stop at the deleted slot. Okay, so take note of that. That's to say that we can insert an element, we can insert an element at that deleted slot. So if we delete a particular key from a slot, we mark it as delete. Okay. However, that deleted slot we can insert there. But when it comes to searching, we can't stop at that deleted slot. So there are some different types of open addressing, and these are based on some functions. Okay, some functions that you need to know. First, we have the linear probing, we have the quadratic probing, and then we have the double hashing. Okay. So open addressing can lead you to 3 other techniques or 3 other algorithms. So the first is linear probing. Okay, so what's the example we just saw concerning the open hashing, okay, with the insertion approach, is known as the linear probing. So in linear probing, we linearly probe for the next slot. For example, a typical gap between 2 probes, okay, is 1. So let hash of x be the slot index computed using the hash function, and s be the size of the table. Okay. So it says here that if slot hash of X mode S is full, okay, then we try H of X plus 1. Okay, so the size of a table is S. So if the hash of X, that's the hash value of X. So if the hash is 2, or in our case, the hash value was 9. Okay, so if that 9 is occupied, that's index 9. Okay, and our size was 10. If that 9 is occupied, we add 1 to the 9, thereby moving us to the next available position. That will give us 10, but we don't have an index of 10. Okay, that's how come we came back to what? 0, because 0 was the position, the available position. Okay, now it's saying that if H plus 1 or hash X, that's this one, if this is full, it's also full, then we do what? Hash X plus 2. That means that if the position which was given us index 0, now we add, instead of adding 1 to the 9, okay, we now add 2 to it to give us 11. Okay. So we move in that order. Then if hash X plus 2 is full, then that means that we are going to do what? 9 plus 3, which is 12. So we keep it in that position 12. Okay. So in our case now, we are going to take position 2 and position 1. Okay. And position 0. Because we are going back into, or we are looping the array, okay, to find the slots that are available. Any question? Any questions so far?
No, sir.
So I want to assume we all understand what I've been teaching so far. So
Yes,
if
sir.
I give you some questions, you should be able to answer it. All right. So this is the linear problem explained here. So the key values are 50, 700, 76, 85, 92, 30, 73, and then 101. And our hash function is key mode 7. Okay, so you can see that the hash function changes based on what the values you have. So if we take 50 mode 7 is 1. Okay, so 50 is inserted at index 1. Then we take 700 mode 7. That's giving us, what value would that give us?
0.
700 mode 7, not mode 10.
0, 0.
It's still 0. Is it still 0?
It's still 0. Yeah.
Okay. Okay. So that will give us 0. And then 76 mode 10. Sorry, mode 7. What would that give us?
Yes, 6.
US.
So that'll give us 6. So 76 is stored here. Then we have 85. 85 mod 7
Give us 2.
1.
will give us 1.
No, it will give us
85
one.
mod 7 will give us 1, not 2.
Yes, sir, 1.
Okay. So it's giving us 1. That means we are supposed to store it what here? 85. However, there is collision occurring. Okay, there's collision here. So the next available slot. So that's what we say the hash. You remember the algorithm hash x plus what? 1. If the slot is full, if hash x is full. So our hash x is what? 1 plus 1, giving us what? 2. So we go to the next value, which is 2. That becomes our next free slot. Okay, and then we put the 85 there. Are we following?
Yes, sir.
Yes, sir.
All right, so let's move to the next. And the next one is 92. 92 mod 7. What would that give
Give
us?
1.
1.
Would also give
1.
us 1. Okay, so if it's giving us 1, our hash x is equal to 1. Okay, so when we come here, 1 is full. So we have to do hash x plus 1. So hash x, which is 1 plus 1, will give us 2. So we check 2. We realize that what? 2 is also full. So we do hash x, which is 1 plus 2, giving us what? 3. So 3 becomes the next available slot. So we put our 92 there. Okay. So this will continue anytime there's collision in your table, to use the linear probing to assign the values in that order. Now, linear probing can lead to a problem known as clustering. Okay, so clustering happens when many consecutive elements form groups and they start taking time to find a free slot to search an element. Okay, so it leads to clustering. Then we have the quadratic approach. And mind you, this is all part of the open addressing technique. Okay, so quadratic probing. Now, it said we look for the I2 slots, okay, or I raised to the power 2 slots inside the ith iteration. Now, what does this mean? So this is just a simple technique being explained here. So if, for instance, we take the previous example where we had I think the first value was 50, right, at index 1. And then we had 80 something. Was it 80? What values did we have?
In the
85.
first one was
50 was at position 1, right? And
yes,
then 85, which also had a value of 1. And then 92 also had a value of 1. So it says 0, 1, 2, 3. Okay. And then we had 1 to be 50. So with the quadratic probing, what you do is that you square the value. Okay. So he said if hash x, okay, mod 10 is full. So if the first one we had 50, so no, so 50 is already in our list, okay, which is this. So we take 85. 85 has a hash value of 1, okay, and that one is already occupied by 50. So quadratic probing is saying that if that hash value is full, then we should try what? Hash plus what? Square root of the ith value. Okay, so this will be plus 1 times 1, or 1 squared. And 1 plus 1 squared is what? It's 1, right? Hello?
Yes, sir.
yes,
Is it
sir.
1?
Yes.
Okay, so if it's 1, so that will give us 1 plus 1, which is 2. So we are going to the next available slot, which is 2. So this will now be 85. Okay. Then we take 91. 91 is also giving us a value of 1. Are we all here?
Yes, sir.
It's giving us a hash value of 1 if we do 91, 92 mode 7. Okay. So that hash value of 1, if we use the first approach, this will be full, or the 1 is full, occupied by 50. Then if we use the second approach, as we saw, square or 1 squared, we add it to 1 squared. That is also full, okay, which is occupied by 85. Then we move to the next approach, which says that we should do what? 2 squared. So the hash, which is 1, plus 2 times 2. Take note, we are doing quadratic probing. The quadratic probing, we square the values. So 2 squared, 2 times 2 will give us now 1 plus what?
4.
1 plus what? 4. And that will give us
5.
5. Okay. So we locate that index 4 and 5. So now we come to index 5. That's if it is not occupied, then we put in the value 92. Are we all together?
Yes, sir.
So that's how the algorithm for the quadratic probing, that's how it works. Okay. All right. Then we have double hashing. So as the name implies, double hashing. So we use another hash function that's hash twice the x and look for the I times hash 2x slots, okay, for the ith rotation. Now what that means is that it says let hash x be the slot and index be the slot index computed using the hash function. So if hash x is full. Okay. So back to the same example. This one doing work here. So let me undo, see if we can. Use the same idea to explain this. So double hashing. Okay. I hope you appreciate where I'm starting the explanation from. So we are assuming
Yes,
that
sir.
50 goes to index 1, okay, and then 85. So 85 is also giving us index 1, which is full. It's occupied by 50. So it says what? We try double hashing. Okay. So the double hashing is saying that we have what? Hash x, which is what? 1. Okay. Plus 1, which is this, times what? Hash, okay, 2x. Okay, so we say hash 2x is just a minute. All right, so sorry about that. Let's go on. Hello, are you all with me?
Yes, sir. We are here.
Yes, sir. Yes.
Okay, so let's go on. So we've been talking about the double hashing. So still on this example, 50 is already occupied. And then, or 50 is already occupying position 1. We have 85 with hash value of 1, but it's being occupied already. Okay, so it's full. So we take, it says here, try hash plus 1 plus another hash function. Okay. So what this means is that we should have another hash function. So if, for instance, our first hash function is, what was it? X mode, what? I think it was mode 7, right? Right?
Mode 10.
No, I think it was mode 7.
Mode 7.
Yeah. So we take our second hash function. And then it's a function, so maybe we can say, give it any function you want. So let's say 7 minus x mod 7. Okay, so that means whatever we are going to get for the first mode value, we have to subtract it from 7 to get the second hash value. We have to subtract it from 7 to from the first hash value. We have to subtract it from 7 in order to get our second hash value. Okay, so we are going to get the first one was giving us 1. So if we do 50, let me just draw another table to explain that briefly. So we have our key here. We have our hash of x here. And then we have our hash 2x. Okay. So if our key is, say, 50, our hash will be what? 50 mod 7. That will give us what?
1.
That will give us 1.
Yes, sir.
Then our hash 2 will be 50 mod 7 or 7 minus 50 mod 7. So 7 minus 1 will be 6. Do you get it?
Yeah.
Are you all following?
Yes, sir.
Okay. Then when we take 85, hash 1 will be 1. So 85 mod 7 will be 7. If we do, so that will be 1. Then if we do hash 2, that will be 7 minus x mod 7. Okay, and we know mod 7 of 85 is already 1. So minus 7 would also give us 6. Okay, 92 would also give us 1. The second hash function will also give us 6. Okay. So based on this understanding, let's come back to our example. Okay. So we said that 50 is occupying index 1 and 85 is also giving us what? 1. which is already full. So we are going to try this. Okay. So first we have hash x, which is 1, which is this one here, plus 1, okay, times our second hash function, hash 2x, which is this one, 6, plus 6. So that will give us what? 1 plus what? 6, right?
Yes, sir.
Making 7. So our new position will now be, sorry, we have to come down. So this is 4, 5, 6, 7. So our new position here for 85 will be index 7. Are you following?
Yes, sir.
Okay. Then we take the next value, which is 92. Now, when we do 92 at position 1, is what? Is occupied. Index 1 is occupied because 50 is there. Now, if it is full, we move to the next one. And when we do that for
Sir,
97, yes,
please, after getting the 7,
yes,
are we not to take mode X on the 7 again?
no,
Because of the what is written over there, there is another mode X.
this is what we are looking at. So we are looking at 2 hash functions when we are doing double hashing. We are looking at 2 hash functions. So when we did the first one for 85 mode, please pardon my handwriting. That gave us what? 1, right?
Yeah.
Then for the second hash function, it's 7 minus 85 mod 7. So that will give us 7 minus 1, because this 85 mod 7 is already 1. You get
Yes,
it?
sir. Yes, sir.
Giving us what? 6. So that's why we have here 1 and 6. Okay. So this hash 2 that you are seeing here, hash 2x, simply is what we've done here. That's the second hash function. That's what's giving us the 6. Okay. So when we want to implement it, we have 1, which is hash x. That's the one we have here. Right?
Yes, sir.
Plus. So I'm just putting this in brackets so that you can appreciate it. Plus 1 times hash 2x, which is what? 6.
6. Yes, sir.
Okay, so that's the 6 here. So that will give us 1 plus 6, because 1 times 6 is 6. Okay, plus
Yes,
1,
sir.
which will give us 7.
7. Yes, sir.
So now we are going to put 85 at what? Index 7. Are you following?
Yes, sir.
Yes.
Yes, sir.
Yeah.
Hello, sir.
Yes.
But
Theophilus.
there is another mode X also, or that one it doesn't matter.
Which one?
After the hash 2x, when the bracket closes, there's another mode X that find the mode of the final results.
I'm
From
getting
just
confused.
please, or where you have just circled, where there is hash 2x. Yes. Right after that, there is a percentage sign and x. Yes. Is it not mode x as well?
No, so it's saying we should try this. Okay, so what it's saying here, okay, I get what you are saying. I get what you are saying. So it's not mode X. Okay. It's just saying we should try this. Okay, but we are not finding the mode of that. We are looking at the two hash value. Okay, so if I'm getting what you mean, I'm trying to say that when we get the 7, which is from this part, right?
Yes, sir.
Yes, sir.
We should do mode
Yes.
S.
Yes, sir.
And that would be what? 7. Mode 7. 7 mode 7.
Zero.
And that will give us what?
Zero, sir.
0.
Yeah.
Okay. That's what you are trying to say, right?
Yes, sir. Yes, sir. That was
Yeah.
what I was saying.
Yeah. So you rather go with the okay, maybe I'll check it out. But what I know is you go with this value, okay, and then that will lead you to your double probing. Okay. But I'll double check and be sure if the mode has to affect it again. So I'll double check and be sure if the mode have to affect it. So if that's the case, then this will be 85. The 85 will go to index 0. And when we do it for the 91, the page looks clumsy. Just undo. All right, so when we take 91, 91 will also give us, if we follow the same approach, we'll end up at the position of 85. Okay, so we try this, which is looking at h of x, which is 1, plus this time you have what? 2 times h, h2, that is what? 6. Okay. And that will give us 1 plus 6 will be what? 12.
12.
That'll give us what? 13. Right?
Yes, sir.
That'll give us 13. But this is the case, our key, I think it ends at 9. It ends at index 9. Okay. But I'll confirm whether we have to find the mode of it again. So if we have to do that, that'll be mode 13 mode 7.
7. Yes.
Okay, 13 mode 7. And what should that give us?
6.
13 mode 7.
US 6.
It will give us 6.
Yes,
Yeah.
sir.
Okay. So that will give us 6. Okay. So I'll do that check, give you the feedback on whether it has to be, you have to find the mode of it again, or you go with the response. So that explains the hash, the double hashing. I don't remember. So in this, when we're doing this, did we find the mode of it again? The quadratic and the linear. I think we found the mode of it, or
No, sir.
we didn't. Oh, okay. Then I'll check. I'll check from the. I'll make that check, because if we didn't find the mode of it again, then I don't think with the double hashing we have to. Yeah. All right. So let's do some comparison. So the linear probing has the best cache performance, but suffers from clustering. Okay. So one advantage is that it's easy to compute. That's the linear probing. Then we have the quadratic probing, which lies between the two in terms of caching and then clustering. Then the double hashing has poor cache performance, but there's no clustering if you do the double hashing. Then there's even the the cubic probing as well, which is can also be considered as another technique to in there. Okay, so based on the performance and the addressing, it's almost 12. Let me go through the last approach, which is chaining. So chaining also is a way of handling collision. So chaining simply use the linked list approach. Use the linked list approach of records. So chaining is simple but requires additional memory outside the table. Okay. So that's as we did when we're looking at the graphs, where we did the adjacency list. Okay, it uses the same concept. So the same example here, the hash function key mode 7, you have the sequence 70, sequence of keys 50, 700, 75, 82, 92, 85, 92, 73, and then 101. So you notice from the example that 85 had a key value or a hash value of 1. Okay, so we do a linked list. So a link leading to 85. So this time around, you do not assign it to any other index. Okay, rather you add it to a chain. Okay, add it to a chain. So it's still the same index. Okay, however, dynamic memory is allocated for that particular value or for that particular key, and it is added to the chain. Okay, so it is linked to this value, a form of a linked list. So we can see how, so this 92, so 92 is added to that chain to form a linked list. So some advantages when it comes to chaining, it's simple to implement. The hash table never fills up. Okay, unlike the open addressing where the hash table will fill up or leading to clustering. Okay, the chaining doesn't lead to, or the table doesn't fill up. Okay, but you can always add more elements to, you can always add more elements to the chain. Now it's less sensitive to the hash function or the load factor, and it's mostly used when it's unknown how frequently keys may be inserted or deleted. Now, some advantages, the cache performance is chaining is not good, as the keys are stored in linked lists. Open addressing provide better caching, like we saw in the previous example. Then there is wastage of memory or space. So some parts of the hash tables are never used if you are following the chaining approach. Then if the chain becomes long, then the search becomes big O of n in its worst case. And then it uses extra space for links. Okay, so this can even be linked to the second disadvantage. Now, the performance of chaining can be evaluated under the assumption that each key is equally likely to be hashed to any slot of the table. Okay, so this is the chaining approach. So difference between the two, like we've said, chaining is simpler to implement, hashing requires computation. Chaining, the hash table never fills up. Open addressing may become full depending on the probing or the type of hashing you are performing. Then it's less sensitive to the hash function load factors. Okay. All right. So let me see. Yeah. So some more differences between the two. Okay. So I'll end it here. I want you to read on some key things. What's its load factor? So go and read on load factor. It's been mentioned in one of the example, load factor. Okay. It's just a simple concept. Then we have what is called secure hashing. Secure hashing algorithm. Okay, so go and read on that one. SHA, secure hashing algorithm. And then secure hashing algorithm and MD5 algorithm. And MD5 or MD5 hashing or MD5 algorithm. Now, these two type of hashing are used MD5, that's message digest algorithm 5. Okay. These two hashing techniques are used lately, especially when it comes to cryptography. When it comes to cryptography. So go and read more on them. Basically, just understand how they work. Okay, whether they are how they work. So for instance, the MD5 works with 32-bit hexadecimal numbers. So the hash value or the hash the hash function produces a 16 by or 128 bits hash value. Okay, that's the MD5. Okay, then there are some key characteristics to it, how they are used, and then look at the security concerns with this algorithm. Okay, then the secure hash algorithm also. There are different variants of it. So also know how they work. What are the main characteristics? They are how secure these two algorithms are, and then understand the concept of load factor. Okay, in terms of hashing, if we say load factor, what does it mean? Okay, all right. Any question? I'm done. Any question?
No, sir.
No, sir.
All right. So next week we'll have, I think, maybe that will be our last face-to-face meeting. Okay, so we'll be having our mid-semester exams next week. It's going to cover everything, including what we studied today, hashing. Okay, so I'll send you the slides, and then you'd have some problems in the slide. Okay, so